So our last lesson for this unit, going further into areas, is going to talk first about irregular areas and how to do some approximate calculations, and then also looking at some solid geometric figures, in other words, volumes of what you've probably seen to be pretty standard shapes, okay? Spheres, cones, cubes, stuff like that. So starting with irregular areas, okay, so we know calculations for common shapes. We talked about squares, rectangles, circles in our last lesson, as well as a trapezoid, okay? So this approximation, the first one we're going to talk about is known as the trapezoid rule, okay? And it's kind of exactly as the name suggests. It uses trapezoids to calculate the area within a shape. In other words, you start with a shape like this. As you can see, each of these forms a trapezoid, okay? Remember, the only thing to consider for a trapezoid is that the two bases are parallel to each other. So what you do in this is you basically measure straight lines, okay? In this case, these are straight up and down. And for this rule to be the easiest calculation, you keep the height, or in other words, the distance between these two lines, the same at each point. Okay, so you're doing regular intervals measuring the distance. Okay, and what this creates is it creates a bunch of different trapezoids. In this case, we have 1, 2, 3, 4, 5, 6, 7 trapezoids. All right, so if you add up all of those areas, you'll get an approximation for what the overall area is. And you can see why it's an approximation. This has a lot of rounded curves. So you can see this line connecting these two together is missing this little bit right here, and this little bit right here, and this little bit right here. But it makes it up, okay, by when you're drawing a line here, it's also adding this little bit of area and this little bit of area, okay, that wouldn't otherwise be in it. So again, it's an approximation, and as with most of these approximations, as you add more and more and more trapezoids, in other words, this value of h becomes smaller and smaller and smaller, your trapezoids will have less room for error, okay, because they'll be closer to your previous point. That's actually something we won't talk about in this course, okay? That actually is kind of a precursor for talking about limits and calculus, okay? So we won't talk about that in this, we're just going to talk about the trapezoid rule. So remember back, the area for a trapezoid is 1/2 times the height. In other words, that's the distance between the top and bottom pieces, or the two parallel lines, multiplied by the length of the bottom and the top base. So in the formula, we called it base number 1 and base number 2, okay, so B1 and B2. In this case, looking at our first trapezoid, that'd be equal to 1/2 times the height times y0 plus y1. Okay? And each of these y's are measurements that you took. So you start with y0, your first measurement, y1, y2, this would be y3, y4, and you keep going, and you can keep doing this forever and ever until you get to your last couple measurements. So yn would be y to the 7, or in other words, the number of trapezoid areas you're going to calculate. So 1, 2, 3, 4, 5, 6, 7, just your dots on each one of them. And then you have your last two measurements, y6 and y5. Okay? So what this means is, if you look at this as a formula, for each trapezoid, the total area would just be the sum of the areas of every single trapezoid. So the area would be equal to 1/2 times the height times our first trapezoid, y0 and y1, plus the area of our second trapezoid, 1/2 times the height times y1 plus y2. Okay, and continuing to mark these, we have y3, y4, y5, y6, and y7. So you can see that the last one is y7. So the one directly before it would be y to the n minus 1, or in other words, 7 minus 1 gives you 6. And the one before that is y to the n minus 2. Okay, so these are the last three measurements that you would take. So y to the n minus 2 is 7 minus 2, which gives you y to the 5. It's important when you see our final version of this formula. So continuing with this, moving to our third trapezoid, we have 1/2 times the height times y2 plus y3. Again, what we're assuming here is that the height is the same for all of them. And that is an important distinction in this formula. And every version of question that you might get that involves the trapezoid rule, this value for h, the height will always be the same. Okay? In other words, we'll have equally distanced measurements. Okay? Continuing this, our fourth trapezoid, 1/2 times the height times y3 plus y4 plus 1/2 times the height y4 plus y5. Okay? All I'm doing is taking the two bases plus 1/2 times y5 plus y6 plus 1/2 times y6 plus, times the height times y6 plus y7. Now, going back to what we've learned about factoring, okay, we could technically factor this value of 1/2 times the height. Okay, we learned it in a previous course, not in this one. So your area is equal to 1/2 times the height. And now you just have everything left in these brackets. y0 plus y1 plus y1 plus y2. I'm just taking the values from each of these brackets now that I've factored out the 1/2 times the height, and I'm just adding them together. Plus y2 plus y3 plus y3 plus y4 plus y4 plus y5, okay, this one, plus y5 plus y6, and our last trapezoid plus y6 and y7. What you'll notice, okay, is there's groupings of 2 for all of these middle trapezoids. 2 of the same length. And the 2 outer dimensions are only used once. And that makes sense, right? You go back and you look at this diagram. For the first trapezoid, this height y0 is only used once. But this height or length, okay, y1 is used for this trapezoid and for this trapezoid. And that continues, right? y2 is used for this trapezoid and this trapezoid. All the way down to our final trapezoid, where that top dimension, y to the n, or in this case y7, is only used once. Okay, and that's common throughout our formulas. So what this means is our area is actually equal to 1/2 times the height times our first measurement, y0, plus 2 times y1, plus all the way through, it's 2 for all of them, okay, until we get to our last ones. 2 times y to the, we call it n minus 1, or in other words, the second last of our measurements, plus our final measurement, again, because it's our final trapezoid, is only used once. So it's y to the n, okay? And what this means in the middle here, whoops, I'll do it in a different color, is that it's just plus, and it's always going to be 2 times that measurement all the way through for all of these trapezoids in the middle, whether you have 4 or 6 or 10 of them, right? This formula just gets longer by adding 2 times all of those dimensions, 2 times y2, 2 times y3, 2 times y4, all the way until you run out of trapezoids and you're on your final one, okay? So let's take a look I'm going to do one example with the trapezoid rule, just to show you what I mean in this calculation, before we talk about a second rule that actually is slightly more accurate than the trapezoid rule. So, the widths of a kidney-shaped swimming pool were measured at 2-meter intervals as shown in the figure below. Calculate the surface area of the pool using the trapezoid rule. Okay, so we'll start with our formula. The area is equal to 1/2 times the height times our first measurement, y0, plus 2 times y1, plus all the way down to our second last measurement, 2 times y to the n minus 1, plus our final measurement, y to the n. Okay? So what you do is you just start here from left to right. Okay, so our first measurement is 0.24 meters. And our last measurement is 0.18 meters. Okay? And our distance in between given in the question was 2 meters. So you look at each of these dimensions and you just start filling in the formula. So the area is equal to 1/2 times our height, 2 meters, times our first measurement, 0.24 meters, plus 2 times our second measurement, okay, going back to this, 6.4 meters, plus 2 times all of these measurements until we get to our final measurement of 0.18 meters. Okay, so 2 times our next measurement, 7.4 meters, plus 2 times 7 meters, plus 2 times 6.1 meters, plus 2 times 5.2 meters. Again, I'm just going left to right here. Plus 2 times 5 meters, plus 2 times 5.1 meters. And now we're at our final measurement. So it's plus just 0.18 meters. Remember back to our discussion on the trapezoids, the first and last trapezoid, that top measurement is only used once. Okay? So for this question, if you calculate this out, you get an area of, we have 1/2 times 2 meters, okay? And summing all this up, you get 84.82. And if you multiply this out, you get 84.82 meters squared. And that's simply because if you look, the 2 meters divided by 2 would have canceled. Okay, so the formula is long depending on the number of trapezoids you have, but in terms of entering data, you're simply just plugging in the data you have into the formula and finding that solution. Okay, so adding all these numbers up and coming up with a solution. There really isn't any tricks to it other than knowing that the first and the last measurement are only multiplied by 1 and not 2. Okay, that's the only trick to doing or to using the trapezoid rule. The next rule is called the Simpson's rule. And the Simpson's rule is a little bit more accurate, especially if you're looking at irregular shapes that don't have perfectly squared edges, okay, that might have rounded edges. Lakes are one example of that with some rounded edges. And Simpson's rule, I won't go through deriving it. I'm just going to explain it to you in the same terms as the trapezoid rule. It uses multiple parabolas. Okay, so this is the shape of a parabola. All right, it comes to a point, okay, and then it can either go down, or you can see parabolas go up. An example of that you might have seen is the equation y equals x squared. This is an example of a parabola. So it uses parabolas. Okay, it's called Simpson's rule because it was named after a famous mathematician, right, from the 17th century. And the only thing to keep in mind, okay, the formula looks a little bit different. It's 1/3 times that height, okay? And in this case, remember, you're doing the exact same thing in Simpson's rule. You're taking measurements at equal distances, all right? Starting at, all right, point 0, and using the same distance between. So height is always going to be the same here. But in this case, for a parabola, you have two items to keep in mind. The first measurement is multiplied by 4 times. The second measurement is only multiplied by 2 times. And that trend continues. It goes 4 to 2 to 4 to 2 to 4. Okay? And the final one finishes with just being multiplied by 1. Okay? So this trend would continue. You could have plus 2y4 plus 4y5 plus 2y6 plus 4y7 all the way to here. The only thing that has to be kept in mind here is you have to have an even number of widths. Okay, so 4 or 6 or 8 or 10. You can't have an odd number or this formula will not work. Okay, there's no other tricks to this. It's simply taking this formula, substituting the variables in, okay, and in this case following that trend from 4, 2, 4, 2, 4, 2, okay, and inputting the variables appropriately. So let's look at our first example. I'm using the same example from the trapezoid rule, but we're going to look at it in terms of the Simpson's rule using parabolas. Okay, so I want you to see that there is a difference when you measure them each way. So the widths of a kidney-shaped swimming pool were measured at 2-meter intervals as shown in the figure below. Calculate the surface area of the pool using Simpson's rule. Okay, so again, you're going to see a difference, and a kidney-shaped pool would do better using parabolas or rounded shapes, again, because of the rounded shape of the actual item we're measuring. Okay, so items that have a little more jagged edges might be a little more suited to a trapezoid rule, and items that have more rounded shapes are Simpson's rule. In general, Simpson's rule seems to be a little bit more accurate. So we start with our formula. The area is equal to 1/3 times the height times the first measurement plus 4 times the second measurement plus 2 times the third measurement. Okay, I will write the whole formula out here so you can see it. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 measurements, but we have 8 widths here, right? Remember, the number of widths has to be even. Okay, so 2 or 4 or 6 or 8 widths. Okay, so continuing, plus 4 times y3, 2 times y4, 4 times y5, all the way we're going to go to number 8 because we have 9 measurements. Okay, so 8 widths and 9 measurements. Plus 2 times y6, 4 times y7, 2 times y8, or sorry, plus just y8, our final measurement. Okay, so if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9 measurements. We have 9 measurements here. 1, 2, 3, 4, 5, 6, 7, 8, 9 measurements. Okay, so you make sure you have all those measurements. Remember, with it being an even number of widths, you're always going to end with the last measurement being used a single time and the first measurement, okay? And the measurements directly beside it being used 4 times, okay? So now it's just a matter of substituting these values in again, okay? So once you do some examples using Simpson's rule, you'll start to see how the pattern of this formula works. So the area is equal to 1/3 times 2 meters. Okay, that's the height, or the distance between the intervals, times our first measurement, 0.24, plus 4 times our second measurement, 6.4, plus 2 times our third measurement, 7.4, plus 4 times 7, our fourth measurement, 2 times 6.1, plus 4 times 5.2, plus 2 times 5, plus 4 times 5.1, plus our final measurement, 0.18. And if you calculate this out, we get an area of 88.15 meters squared. Now that's very different in terms of measurement compared to the trapezoid rule. So the trapezoid rule got 84.82 meters squared, if you remember from the previous example. So you can see how they vary, and that's because their coverage of areas, specifically, you talk about the areas close to the edge of this pool. Remember, in the trapezoid rule, you had a trapezoid like this, and this, and this, and this, and it missed a lot of these little areas in there, right? So because this is a more rounded object, the parabola, okay, actually covers more of this area. So in this instance, this is actually a better approximation of the area than the trapezoid rule. And that's just given the geometry of the shape that we have. So let's look at a second example. Okay, this is again using Simpson's rule. A parking lot is proposed for a riverfront development. The surveyor measured the width in 30-meter intervals as shown below. Find the area available for parking using Simpson's rule. So remember, we have to have an equal number of widths to use Simpson's rule. Okay? So we have 1, 2, 3, 4, 5, 6. So we do have an equal number of widths. Right? So we can use this rule. And in this case, we have 1, 2, 3, 4, 5, 6, 7 measurements. Okay, so we'll start at point 0, and we should get to y6. Okay, so our area is equal to 1/3 times our height times our first measurement, call it y0, plus 4 times our second measurement, 2 times our third measurement, 4 times our fourth measurement, 2 times our fifth measurement, 4 times our sixth measurement, and then just our final measurement. Let's say 4 times y5 plus y6. Again, we started at 0. Okay, so we're going from 0 to 6, and what that means is the individual shapes from 0 to 6. We actually have 7 measurements here. So now if we substitute these values in, our area is equal to 1/3 times 30 meters. And that's multiplied by our first measurement, 124 meters, plus 4 times 147, plus 2 times 116, plus 4 times 115 meters, plus 2 times 87 meters, plus 4 times 117 meters, plus our final measurement of 144 meters. Again, all I did was take these values and simply substitute it into this equation. So if you add all those together and multiply them out, okay, you get a total area of 21,900 square meters. Okay, again, looking at this picture, Simpson's rule was a good approximation given the unevenness of the riverbank close to this development. Okay. So now that we've talked about areas of common shapes, we've talked about measurement of irregular areas. Okay, what we just talked about was the trapezoid and Simpson's rule. Now we're going to talk about solid geometric figures. In other words, finding the volume of some common shapes. So your textbook shows more shapes than this. All right, I'm going to go through the important kind of basic shapes with you. And we're just going to work through a few examples. Okay, we're not going to do an example of every single shape, but doing the practice exercises after this lesson will reinforce these concepts. Because once you've done it for 1 or 2 of these shapes, the formulas change in terms of how they're multiplied, but they're all used the same. Okay, they're all used the same. You just might have to figure out the terminology associated with each type of shape. Okay. So the 3 I'm showing you here, the first one, they call it a rectangular solid in your textbook. The other way you might have seen this is called a rectangular prism. Okay, I wrote it similar to the way they put it in the textbook because when you start doing the exercise questions, you'll see that they've used that name. All right. So the base for this is actually 2 rectangles. You can see rectangle number 1 and rectangle number 2. Your sides for this, on the 4 sides, are all rectangles as well. Okay, 1, 2, 3 in the back here, and 4 on the side. The area for this, all right, is simply the addition, okay, of all 6 of these sides. So if you were to write this out, okay, you'd have the bases, length times width, okay, so in other words, this one, and that's multiplied by 2, right, because you have the exact same rectangle on the top, plus width times height for this shape, and again, you have 2 of them because you have a matching one on the other side, so times 2, plus our final one, okay, length times height. And again, you have the matching rectangle in behind. So length times height times 2. So what you can do is you can just factor the 2 out of these. All right, it's the only item that's common in all 3. So you end up with your area is equal to 2 times length times width plus length times height plus width times height. Okay, so that's the way I've written it here in the table. All right. The next item everybody's seen before, a cube. In other words, a cube is just a 6-sided figure with all squares. So the base, okay, has 2 squares, and the sides have 2 squares, and all sides have equal lengths. So the area of an individual side is s times s, which is s squared. And since all the sides are the same, you just do 6 multiplied by the area of one side, because it's a 6-sided figure, to get the area. So the area in this case is 6s squared. And the volume, okay, is simply s times s times s, right? So the 3 sides multiplied together. Okay, so you get the volume is s cubed. So one item I didn't talk about, going back to the rectangular prism example here, okay, is the volume similar to the cube. It's just simply the 3 sides multiplied together, length times width times height. Okay? It gets to be a little different when you talk about shapes that have circles. The first one, your textbook calls it a right circle cylinder. It is more commonly just called a cylinder. All right? You see cylinders in a lot of instances. One example that stands out is obviously toilet paper rolls. The actual cardboard roll in the middle is a cylinder. Okay, these are quite strong shapes when they're placed on their side, as shown here. You can kind of see that if you were to watch videos of people taking toilet paper rolls and seeing how many they take for you to stand on them. Okay, you actually can stand on that end on end if you have enough toilet paper rolls, the little cardboard inserts. Okay, so they're a lot stronger than they look. So the area for this, all right, if you take the sides, the bases are both circles, okay, and the side of it is just one long curved side. Okay, so picture pulling foil off of an aluminum foil roll, okay, and pulling it out, all right, to match that circumference. That's the area of that outer piece, okay? The formula for surface area for this is 2 pi r, okay, r being the radius of the circle, multiplied by the radius plus the height. Okay, so that's just a formula for you to remember. The volume is simply the area of the base, so pi r squared, multiplied by the height, okay, h. So that's the easiest way to consider when you're looking at volume for a cylinder, okay? So the other 3 figures I'm focusing on are the cone, the rectangular pyramid, and the sphere, okay? So you've often seen the rectangular pyramid. You can also see it written as Some people have seen it as a rectangular prism, right? It just depends on kind of the notation in a textbook or kind of how you've learned it in high school. So starting with a cone, okay, so a cone has a base, okay, that's a circle, and the side, just like when we talked about a cylinder, if you were to pull that aluminum foil, all right, or pull plastic wrap or pull any of those items on a roll, okay, it makes a single kind of curved surface. The difference with a cone is that it comes to a point at the top, okay? You've also seen these if you see them wrapped up and it's a paper cup, that you might get the dispensable paper cups for drinking, or paper cups you might use if you've gotten snow cones before, okay? So the surface area for this is simply pi r squared, which is the surface area of the base, plus pi times the radius, okay, in other words, to get a circumference, times s, s being the length of this long side, okay, of the cone, okay. So you're basically, if you were to unwrap that side of the cone, you'd be left with s, and the length of it would be the whole circumference of this circle if you were to unwrap it the entire way. Okay, that's kind of how I visualize surface area. Volume is a calculation. I'm not going to go into how it was derived, it's just one that you need to know. It's 1/3 times pi r squared times the height. The height being from the center of the circle directly up to this point. Okay, so the height is a different value when compared to s, which is that outer length. Okay, the height will be smaller, and again, that goes back to Pythagorean theorem, where s here is the hypotenuse, okay, and h and r are the opposite and adjacent sides. Okay. A rectangular pyramid or rectangular prism has a base of a rectangle, okay, and it has 4 triangles, okay, 4 equal, okay, so you have 4 triangles. They're equal if the base is a square. They're not equal if the base is a rectangle, okay. So remember, a square is a form of rectangle, and just in which all 4 of these base sides are the same. So a couple of dimensions I haven't written here because I want to explain those to you. Okay, so this is your length. Okay, call it L, and L will be the same on adjacent sides, just like it was in a rectangular prism. And width, the other side here, okay, again the same on the opposite side, just like a rectangular prism. So your area is just the sum of these 4 rectangles, okay? Sorry, 4 triangles plus the rectangle at the bottom here, okay? So if you were to actually, you do this as a formula, your area would be equal to length times width, okay? That being the area of the base rectangle, plus the area of the 4 triangles. Remember, 1/2 times the base. So if we start on this triangle here, we have length times the height of that rectangle, remember, is s, okay, because that s here is actually the dimension of the rectangle, starting from the center of the rectangle all the way up. So it's L times s. Plus our next, just going around the rectangular pyramid, our next one would be 1/2 times our base, which is width, times, again, s, okay, which is the height of the rectangle, from the midpoint of the base to the tip. Plus our third triangle, 1/2 times the length, okay, I'm talking about this back triangle here, times our height, which again is s. Remember, it's s for all of them because they come to the same point here. Plus 1/2 times our final triangle, which is the width, W, multiplied by S. Okay, so what you can see here is you have 1/2 times LS and 1/2 times LS. If you add 2 halves, you get a whole, or 1. And the same thing is true for 1/2 times WS, or the width times S, plus 1/2 times the width times S. Okay, so you can add them together, and you end up with this formula here. Length times width plus WS plus LS. Remember, because 2 halves make a whole. For the volume, we use a different value, just like we did in the cone. We use the height, which is from the middle of the base of the rectangle up to that point where all the triangles come together. That's known as the height, and we denote that as H. The volume is length times width times height, okay, just like you saw for a rectangular prism, but it's divided by 3. And if you stop and think, that makes sense, right? Because this is coming to a point at the top. It's not like a rectangular prism that's going to come all the way up the entire way. Okay, so you don't have all this area that the rectangular prism would have had. So that's where that divided by 3 piece comes in, because it's removing that additional area. If it was just length times width times height, it'd be the same formula as a rectangular prism, and it would be incorrect. Our last one, okay, is a sphere. So for a sphere, it's just one curved side, okay, and you see it as just having kind of a circle. It doesn't really have a base, so to speak, right? The base is kind of a point, all right? And the area for this, again, these ones I won't derive for you, all right? And the reason I'm not going to derive these ones for you is I just want you to have this formula so you understand it. So the area of it is 4 pi r squared, or 4 times the area. The volume is 4/3 times pi r cubed. R, in this case, is the only variable we have for a sphere, and it is the radius. Okay? So simple formulas, ones you just need to remember. So let's look at our first of 2 examples. Okay? So I'm going to show you is there are going to be 2 different shapes in each example. And our exercises I'm providing for you in the textbook will go through the rest of the shapes. But just keep in mind that the method of solving these is the same regardless of the shape. Okay, so what you see and how I approach these questions, this one and the next one, will inform how you do the exercises in your textbook to practice other shapes. The spaceship Earth at Epcot Center at Walt Disney World is a sphere with a 50.3 meter diameter. What is the volume? Okay, so what the question is asking is volume. Okay, this picture on the right is actually that spaceship Earth sphere at Epcot Center. Okay, if any of you have been there, it's pretty large in person. It's been a while since I've been there. So we start with our volume calculation. Our volume is 4/3 times pi r cubed. So we need the radius, and we have in this question the diameter. So the diameter is 50.3 meters. And remember, the diameter is all the way across, okay? And that means we have the radius on both sides. The diameter is actually equal to 2 times the radius, right? So this whole length is the diameter, but it's actually equal to the radius times 2. So we have 50.3 meters is equal to 2 times the radius. So to solve for radius, we divide both sides by 2 to get radius by itself. So the 2's on the right-hand side would cancel. And your radius is 25.15 meters. So now that we have it, we can simply substitute it into our equation. So our volume is equal to 4/3 times pi times 25.15 cubed. And if you calculate that out, you get 66,635 meters cubed. So a very large volume for this dome. Okay. Our next question, a paper cup is the shape of a cone, as shown in the figure below. How much liquid can the paper hold? Okay, so I asked how much liquid. You might think you have to convert it to milliliters or liters. You can do that. If you looked at my solution, you'll see that I have converted it to milliliters. I would accept the answer as just a volume calculation in any units. So centimeters cubed, because that's what's given in the question, would be acceptable. If you do convert it to milliliters, oftentimes on these questions, I would actually give you a bonus, because that's something that I don't cover in this section, is doing unit conversions, but they're one of the most useful tools you'll need to know in the workplace, especially since a lot of you will be working here, and our data in Canada, a lot of us try and work in metric, especially when you talk about in the civil world. In the mechanical world, a lot of items are still done in imperial, so in inches and in pounds and in feet, which are not as intuitive of measurements, but you'll see that they're very common just because our neighbors to the south, the United States, use only imperial. That also includes temperature being something like degrees Fahrenheit. There's something to keep in mind, that if you do know how to do these conversions to milliliters, or those conversions, and you do them in the question, I'd probably be looking at giving bonus marks for that. So starting this question, it's the shape of a cone. Okay, and we're asking for how much liquid can the paper cup hold. In other words, what is the volume of it? All right, so going back to our formulas, the volume is equal to 1/3 pi r squared times the height. Now what we have in the question is the height is 8.90 centimeters, but the value we have here, 9.20 centimeters, is the diameter. And remember, we need the radius in this question, and the diameter is 2 times the radius. So 9.20 centimeters must equal 2 times the radius. So to solve for radius, we divide both sides by 2. Okay, so the 2's on the right side cancel. And our radius is 4.6 centimeters. So now with the radius and the height, we can simply substitute those values in. Our volume is equal to 1/3 times pi times our radius, 4.6 centimeters, squared, times our height, 8.90 centimeters. Now remember, these are both in centimeters, so it's okay. But when you're doing these volume calculations, you have to have the same units. They have to all be in centimeters, or all be in meters, or whatever unit you're in, or you won't have a volume calculation that's cubic, okay, or to the exponent 3. So if you calculate all of these out, you get a volume of 197.2 centimeters cubed. And again, a great thing about metric, I use both extensively in the workplace, metric and imperial. Imperial I actually had to learn while in the workplace. The beauty of metric is for similar units, it's a 1-to-1 conversion. So a centimeter cubed is the same as a millimeter. So 197.2 centimeters cubed is the same as 197.2 milliliters. That's converting it to a liquid. So again, that's the benefit of, you'll see, in one of the many benefits of using metric units instead of imperial. Right? Again, I'm okay with you leaving it as centimeters cubed, and you'd probably have bonus marks for doing a conversion like that. So that's all there was for this lesson. These are the practice problems I highly recommend you look at. Again, for geometric figures, and it'll show you different questions with different shape types. We did 2 examples in this lesson. So keep in mind, please do these questions. You can try other questions if you want, but I don't necessarily expect you to be able to do them, because I picked these ones specifically based on what was taught in this lesson. Okay? If you do have any questions, please bring them to our tutorial, or send me an email, and I'd be pleased to answer them. Thanks, everybody.